I would like to welcome all the participants for the seminar, either face-to-face. I think I have about 10 to 15 participants in this meeting room. And then the last I checked from online, I have about 70 plus participants. We have about 70 plus. So I hope this seminar will be beneficial to you. Of course, this is not a complete or a full seminar. It's just to, as an introduction or a precursor to understanding what are the capabilities of PVSyst and how you can benefit from using the software in your PV system design. So from the survey or from the registration form that I have gone through, I found out there are quite a diverse range of participants from students, from industries, from other universities. And I believe all of you have different backgrounds in terms of the rate of using PVSyst. Maybe some of you have no prior knowledge or background in PV and would like to learn something from this seminar, while there are also maybe somebody else at the end of the spectrum who are already well versed in using PVSyst, but may join this for some other reasons, maybe want to refresh or something. So anyway, I try to balance my presentation to cater this wide number of participants or wide range of participants. And I sincerely hope you can benefit from this seminar. Okay, so before I proceed, please allow me to go into some introductions. This is a bit background on myself. I won't go too far or too detailed. So I am a certified SEDA trainer for the SEDA GCPV course for wireman and chargeman. And I am also a certified SEDA Malaysia Grid Connected Solar PV designer. Prior to SEDA, there was also another certification, which was ISPQ. I also had the certification until SEDA took over for the certification process. So I have been involved in research and training officially since 2015. And we have in quite a number of wireman and chargemen. So for the competency course, so these are among the companies that have been kind enough to join our training group. We have from TNB, we have from SunPower, Honda. We even have participants from Shorefield in Sarawak, I believe, and many other companies. And just to provide some information, in our lab, we can cater for multiple levels of training in GCPV, from beginner level up to maybe advanced level. And here are the list of available training equipment and facilities currently available. Right. So before I begin, I would like to acknowledge that for the PVSyst license, we have managed to purchase the license from the grant provided by Zingi, which is a company that is manufacturing solar panel glasses based in Malacca. Well, one of the company is based in Malacca. And this is my research group for the grant, which is led by Associate Professor IR Dr. Gan. Right. So a brief introduction on what we have. Currently, our system is relatively small. It has been around for about 10 years already. We started around 2013. So currently, we have this system comprising a 28 kilowatt peak grid connected system. We have different technologies because at the time we want to study what are the effect of different module technologies on the power output and how we can benefit and optimize from all of them. And we are also one of the 6 training centers in Malaysia that is approved by SEDA to conduct the grid connected PV solar systems for chargemen and wiremen. So currently we have 4 qualified personnel. We have 2 qualified SEDA trainer, which is myself and Associate Professor Dr. Gan. And then we also have two competent SEDA judgment, which is Mr. Yusri and Mr. Wahyudi. So my name is Dr. Khairul Azmi, but my friends prefer to call me by Dr. Kiai lah. So you can also refer to me by that name, referring to the first four letters of my word, four letters of my name. Okay. This is my center of excellence which I am under, which is Ceria. Okay, the name may be a bit misleading, but there are a few research groups under this. So Ceria stands for Center for Robotics and Industrial Automation. And the vision of this center is to be a referred research group for the advancement in electrical and automation engineering. So our mission currently, we want to conduct researches in new technologies, consultations, testing, and also new product developments. So from the participants, I see I have some colleagues from UTeM, UTeM, UTeM as well. And many of them has also contributed a lot, especially in the field of solar. And many, each has their own research niche areas lah. So we hope that we can further collaborate down the road, and we try to find out what are the best contribution we can give to each other. Okay, so under Ceria, we have the list here for the research group. We have robotics and industrial automation, RIA. And then we have energy and smart grid technology, SGIT. So I am under this research group. And apart from that, we have electric vehicle, power electronics, machines and drive. We have rehabilitation engineering and assistive technology. We have electrical asset condition monitoring, and we also have drone technology. So if you guys are interested or are directly involved in these fields and are looking for collaborative partners, you can contact us later. I will provide you the links afterwards. Okay, here are our programs and activities. So natural to every type of university, we are focused on research, and also we want to have testing, training that are relevant to the industry. We are also interested in university-industry collaboration. We like to contribute into the production of new technology or new devices. We provide consultation and services to various fields as related to the research groups just now. And we also conduct short courses from time to time depending on current needs and requirements. And on the right-hand side of the slide, you can see our current international and industry linkage. We have linkages from industries, international universities, and so on. And we look forward to create more international and industry linkage in the future. Okay, that's it for my introduction. Let's not waste time, and let's move on to the content of the seminar. So this is the objective. I set only 3 simple objectives. So the first one, I want to share with you how to design a simple grid-connected PV systems using PVSyst. And we want to generate from start to finish until we get a simple report. And we want to know how to read and understand the report. That's the first objective. And then the second one, to provide some background theory for the steps. So not all of us are from the solar background. So when we want to do the simulation, there are some theories required for us to understand what the results mean. Okay, so I'll try to compensate that part. And number 3, to evaluate how different design parameters affect the system performance. Now, when we design, we usually start with a base case, one case, and then after that, we always look into how to improve the design. We play around with the values, we change the configuration, we do some things, and then we try to see what is the effect on our design. So from there, when we change the design parameters and we analyze the result, that is how we improve our design process and produce the best system design. So that is my target for today, and I hope within this limited amount of time, about 2.5 hours, we can achieve that. All right, so now let's move on to the website itself for PVSyst. Now, if you type type in PVSyst.com. Hold on, I think I should. Okay, so you can type, if you are in front of your PCs or computers, you can type PVSyst.com to access this website. A lot of information is already available here. If you would like to download the software, you can click at the download tab. So there are some installation requirements needed. You need to install it on a personal PC or a dedicated PC. You cannot install it on a server. That is the requirement for PVSyst. And currently, PVSyst only runs in Windows directly. So if you want to run in, for example, a MacBook, so you need to have a virtual machine. Okay, so these are the installation requirements listed or posted in the PVSyst website. Okay, some required computer configuration. I think this one you can go through on your own, depending on your computer capability. And if you are interested, you can download the trial version. So the trial version allows you to use the full capability for 1 month, full features, and you can, of course, you can. If you want to follow this seminar hands-on, some of you may prefer hands-on session, step by step, so you can install it on your own. Right. Let me show you a bit about the licenses available. So currently for us, the license is quite expensive. Okay, and also it's not a perpetual license. It's an annual license. That means we need to renew every year. However, the features are very powerful, and if you are directly involved in the PV field, then the investment for this software might be beneficial and profitable to you. Okay, so the subscription for a professional version is 600 Swiss franc. This is in Switzerland currency per year. Around 3,200 ringgit, around that value, around that amount lah, the price. And they have several discounts. So currently, we in UTeM, we managed to get the education discount lah, 40% discount. But we, of course, when we have this kind of license, we cannot conduct, paid training. But this one is a free seminar, just as a knowledge sharing, so I don't think it's a problem. If you are involved in research, or if you would like to conduct training yourself, so you can purchase the licenses under these discounts available. Right? Okay, so let's look a bit of about the features of this software. Okay, this information is available on the website itself. You can go through later on. So of course, when talking about the full spectrum of the available features in PVSyst, we cannot complete exploring it in 1 or 2 days. But at least we can find what are the fundamental design process required. So these are the advantages of using this software. So we have system design. We can design a system from scratch, even with minimal knowledge on the theory behind combining the PV inverters and PV modules and so on. We can still conduct with acceptable amount of reliability. Okay, and then we can conduct system sizing, which I'm going to share this one. So we can scale our system according to the size or the area that we have. Okay, and then this one is complicated, a bit complicated, which is shading. Because we know solar panels, the output is directly related to the amount of sunshine that hits the module surface. So if it is shaded, I mean, if it's part of the module or all the module is covered, let's say by the shadow of nearby buildings or trees, it's going to directly impact the power output. But sometimes in your design, these things cannot be avoided. Let's say you got a project, you need to design your solar system, but there are already objects or buildings around that you cannot do anything about. So you need to have this kind of shading analysis to know what is the actual power output that can be produced under these conditions. So it's a bit complex because shading changes throughout the day depending on the movement of the sun, and also changes throughout the year because the position of the trajectory of the sun changes every day. This one is not covered in this session, but I'm going to just provide a brief overview of what the capability of PVSyst. Okay, and then we have simulation results. This one is important. We want to know what we can understand from the report that is generated. Okay, grid storage. This is currently the trend. Malaysia is in the process of having our grid connected combined with storage. So the previous minister planned us to have a storage combined with grid connected PV systems by 2030, which is about 7 years time. We want to wait for the price of the storage to go down first before we try to integrate with the grid. But it's already available in PVSyst because many other countries have already deployed it. Okay, we can study about, let me just go through highlights some of the things. We can study about aging so that we know after 10 years, 15 years, what is the expected power output. Because of course, after degradation, we can expect the same power output throughout every year. So we need to consider this is important, especially when we want to consider the cost. Because usually for solar PV system owners, they are paid based on the rate. Cannot depend on, let's say, the first year, okay, you generate this amount, then the second year you expect the same amount of generation. That is quite unrealistic. So we need to be mindful of that as well. All right. And then some other things, we have economic evaluation, we have optimization and batch mode. This one, if we want to run multiple simulations at one time. Let's see whether we have time to go into this. But I want to cover the basic simulation process first. Apart from grid connected systems, we can also conduct or design standalone systems and pumping systems. But that is beyond our seminar for today. Okay. So if you have the PVSyst already in your laptops, you can turn it on. Or if not, you can also follow. I will go step by step and show you what PVSyst is all about. Okay, so I'm opening PVSyst now. So currently I'm using version 7.4. So version 7.4, not much difference. I think the version 7.4, if you have previous version, 7.4, I think it's upgraded the bifacial analysis for PV modules with bifacial configuration. Bifacial means you have two-sided. Bifacial modules, you have the top and bottom, both can absorb sunshine and generate electricity. Okay, if you have opened this one, this is the layout, the opening layout for PVSyst. We have several options available on the top here. So first of all, we are going to select which type of project we are going to use in our design. Under it, you also have options on the databases and the tools and also the measured data. So if I click on the database, so here are the list of the database available in PVSyst. I don't want to go into details. This one. After I finish the report, maybe if we have time, I'll cover this one. And also the tools. Okay, this is a bit technical, so or rather advanced. So let's leave it at that for now. And then this one is measured data. This one, if we have our own data, we want to input into PVSyst. Okay, on the documentation side, you already have the help files available here. You can directly click. You can type FAQ if to find the frequently asked questions related to the software. And there are also links to video tutorials in YouTube under PVSyst channel. So now I'm going to click Grid Connected. Once you click Grid Connected, you are going to be brought into this window here. So for my case, I've already run projects. So there's already a project name listed there. But if you are running it for the first time, it's going to be like this. So project name, you have new project. And then you have site files and Meteor files. And then after that, you have at the bottom here, variant. Okay, how does PVSyst design is used for design? The word variant or the term variant is a key concept used in PVSyst. Like I mentioned just now, what we do in PVSyst is first, we design a base case. And then after that, we change the parameters under different variants. And then we run again the simulation so that we can see what the changes have the effect the changes have on the design process. All right. So for the project, if you save a file, it is going to be saved under the file name. You can put your own name, or you can put whatever name you like, and then the extension or the dot after the name of the file is going to be .prj. Okay, so for now, I'm just going to provide an arbitrary project name. So I just do demo seminar UTeM. Okay, it does not need to be written in I mean, you don't have to put this underscore. You can put space if you like. Doesn't matter. And you see here, it already provides what are the steps that is required. So the first step before we design is we need to choose the geographical site where we want to install our PV system. Okay, let me go a bit to the background. It's the sunshine that reaches the surface of the solar panel actually comprises of different types of irradiance. So from the top of the atmosphere, we have a solar radiation of around 1,367 watt per meter. The unit is a bit wrong there. Please forgive me. It's actually watt per meter squared. Okay, once the sunshine passes through the atmosphere, the most common types of irradiance is direct solar irradiance. That means we have direct from the sunshine through the solar module without any obstruction. So we call this as direct normal irradiance. And then we also have solar irradiance that is not directly from the solar, but rather comes from another source. For example, the sunshine passes through clouds before reaching the solar module. Or maybe the sunshine hits the ground and after that reflected to the solar panel. So those kinds of solar irradiance is a bit reduced or diffused. That means the intensity is lower than direct solar irradiance. So we call it as diffused solar irradiance. diffuse solar irradiance. And then the total between direct and diffuse, we call it as global irradiance. So the terms here, global horizontal irradiance, because the irradiance is measured horizontally, flat, with reference to the Earth's surface. Okay, same like here, diffuse horizontal irradiance, while direct normal irradiance is because we refer to the sunshine directly hitting the solar module, which is at a normal angle. Okay, this is a graph that shows a sample of a daily irradiance profile. So we have the curve with the triangle markers refer to the direct irradiance. So about 90 to 95% of the amount of irradiance that we get comes from direct irradiance. While the rest, around 5 to 10%, comes from the diffused irradiance, which is indicated by the line with the circle markers. And the global horizontal irradiance is actually the combination between direct and diffuse. Okay, so that is the background. So choose the geographical site. So the geographical site is important to determine the amount of available sunshine. Okay, let's go back to the software. So here we have a site file. So in the site file, sorry. Hold on, yeah. Here we have the site file, and at the end of the screen here, we have some options available. So we can, if we click the folder here, it's going to produce a list of available files or available sites already in the database. There are about 2,500 sites already available here. And for example, if I type Malaysia, it doesn't come out. It's just highlighted what are the sites currently available in Malaysia. But we need to scroll down a bit lah. Okay, some of the sites is here because I already put it in my simulation before. So if we want, we can find if there are available sites here. But I'm not going to use this one. I'm going to directly select this icon here, which is the new site. So I'm going to click this one. So if you run this software while being connected to the internet, you can access this interactive map. If you are using this software without internet connection, then this interactive map will not be available. Okay, so this is a very handy feature when you want to select the location where we have multiple options available. For example, we can use the interactive map to find where we want to put our PV modules or PV system. Okay, so the default location is set in Switzerland because that is the basis of the software. So we can scroll to find Malaysia, and then we can select the location by zooming in. But this is also quite tedious, in my opinion. The other option is we can use the locality option available here, and we can type. For example, I type UTeM Melaka. Okay, not found. So maybe I type Melaka only. Okay, so it can determine Melaka. We can zoom in. And it provides a location in Bandaraya Melaka. For me, my personal choice is actually to key in the coordinates here. So for example, let's say now I want to find the coordinates for UTeM. So I have this value here. So I want to use this value directly. I can select the coordinates and put it here. And I press enter. And it already provides the location, the exact location in the map. I can zoom in now. If you did not set in earlier, it will directly automatically point to the direction of the coordinates that you choose. Okay, so if I zoom in, I have the coordinates pinpointed here. So even we can, apart from this, we can also set a pin in the interactive map. Let's say now I want to install not here in Chancellery, but rather here. This is the Faculty of Electrical Engineering. I can just put a pin there and the coordinates will update automatically. Okay, then after we have selected our location, it will provide the basic information on the right hand side here, which is the latitude, the longitude, and the altitude as well, and the time zone. Okay, I'm satisfied with the current setting, so I accept the selected point. So it has already given a site name based on the coordinates that I have keyed in just now, which is Kampung Ulu Padang Keladi. But I don't want to use this, so I want to change it into FKE UTeM. Okay. If you don't have internet connection, then you can also already key in the coordinates directly here. From the window here, you can put in the latitude. You can type in the latitude and longitude, and you can also get the coordinates. I mean the location that you want. Okay, here on the right hand side, you have the option for Meteo data import, and you have 6 options. Okay, what this actually means is that once you have selected a location, the system, the PVSyst needs to know what is the irradiance profile available at that location. So it needs to refer to some sort of database. So these are the available database that can be accessed under PVSyst. So the first two, Meteornom and NASA, are database that can be accessed online or offline. Okay, which is why they put it on top. The rest, PVGIS, NREL, Solcast, and Solar Anywhere, is need to be accessed online. And I believe software like Solar Anywhere and Solcast, you need to have a subscription to access the data. Okay, so I haven't explored the rest. I only explored Meteornom and NASA website, NASA data. The rest I haven't explored yet. But I believe Meteornom is already sufficient for almost all of your simulation. Okay, so I'm going to select meteonom now, and I'm going to import. Okay, once you import the data, you will be brought to this window, which is, if you look here, it says monthly meteor. This is the meteorological data. And it provides the several important parameters for our design in the form of monthly values. So we have here global horizontal irradiation, horizontal diffuse irradiation. We have the ambient temperature, wind velocity, link turbidity, and relative humidity. And these are the values for each month. So you see, throughout the months, the value of the irradiation changes. And this change is because of several factors. Number one is because of the movement of the sun. Okay, here in Malaysia, because we are located near the equator, we don't feel the difference in the seasons throughout the year. Our weather is about the same. The only difference is we have either, dry season or rainy season, basically. But if we are in the northern European countries or maybe somewhere in Australia, then they experience seasonal changes. They have spring, summer, autumn, winter. So under this condition, you will see that the global horizontal irradiation in those locations have a very significant difference between each other. Okay, however, for us, the changes are relatively small, the differences. Okay, talking about units. If we refer here at the irradiation units, we have several units options available. Okay, the default setting is kilowatt hour per meter squared per month. But let's go explore about the other units. I'll start with kilowatt hour per meter squared per day. Okay, so these are the values. Maybe I try to zoom in a bit for the benefit of our online participant. Okay. So we have January 4.78. What does that mean, 4.78? It means for our location, right, from sunrise to sunset, we have about 12 hours. Let's say around 7 a.m. the sunrise and the sun sets at 7 p.m. lah, roughly, yeah? So we have 12 hours. But actually, the effective sun hour from that 12 hours is only 4.78. Because you see, during sunrise and sunset, the trajectory or the position of the sun is very low. So not much amount of sunshine we can use. Yes. But as the day goes along, so when it approaches noon, the sun becomes higher, and then we have more irradiance. Okay, I have a slide to show you the explanation or the theory. So this is the concept, yeah? So we have sunrise maybe around 6 a.m. Yeah. And then the sun goes up until it reaches the top here at noon. And then it goes down until sunset at around 6, 7 p.m. Okay, this is the shape of the sunshine movement, or the shape of amount of power available based on the sunshine movement. So basically, we want to convert the zones or the area from the outer side here. We want to put it in a box. So we set the maximum limit as 1000 watt per meter squared. And we want to know the area under the curve, the total area under the curve. We set the limit at 1000 watt per meter squared. We want to know how many hours, equivalent hours here. So in this graph, the example is 5 hours. So this is the effective sunshine hours in kilowatt hour per meter squared per day. So naturally, the longer or the larger the value of this daily value, the better our performance, PV system performance will be, the more output we can gain. That's why you see many of the PV systems in Malaysia, a lot of projects is installed in the northern area like Kedah, Perlis, Penang, Perak. Because those areas, if you look at the map, the amount of irradiance is a bit higher compared to us further down south. Okay. Going back to the software. Where was it? Maybe I accidentally deleted. Hold on. Okay. FKE UTeM. Okay, so I'm going to choose Meteor data import here. Meteor norm 8.1. And I'm going to select import just now, like just now. Okay. Apart from kilowatt hour per meter squared per day, so at the bottom here, it provides the average daily irradiance or daily effective sun hours, which is 4.71. And it also states the year-to-year variability is around 6.6%. So there must be some tolerance we need to expect from this one. If we choose the second option, kilowatt hour per meter squared per month, it provides the total amount of hours available. So here in year, you see the number 1719.5. So this is the total hour sunshine available throughout the year for this location. We have other options available. Megajoule per meter squared per day. This one is more related to weather related, meteorological scientists. They usually use the unit of megajoule. If electrical engineers, we mainly use kilowatt hour. Okay. And we also have the bottom here, clearness index. Now, clearness index is actually the ratio of the amount of sunshine that is available from the top of atmosphere and compared to the amount of sunshine that reaches the surface of the earth. Okay, if there is no obstruction, then the value will be 1 or slightly more than 1. But for our location here, because we may have a lot of clouds, so a lot of the sunshine is blocked, right? So the clearness index is reduced. So we see the range of clearness index is around 0.4 to 0.5, which indicates that we have a lot of clouds obstructing. Okay, I'm going to select back kilowatt hour per meter squared per month, and I'm going to click OK. If let's say you have your own data you want to put inside this one, you can select here import, and you can put in your own data. If let's say you have a measuring station, you record this kind of data, you want to put it as the simulation data, then you can do this. But I'm going to stick to this one. Okay, so I have FKE UTeM. Okay, I'm going to click save. And then this window pops up, a synthetic hourly meteor file has also been generated. This basically means that the available data is monthly data, but using some formulas, some equations, and some extrapolation, they generate a synthetic hourly data so that they can conduct a more accurate assessment. Okay, I'm just going to click yes, and I'm going to click save. Okay, now it comes back to the project window, and we have here selected meteor file, this one. Please save the project. So I'm going to save the project. Okay, now we come to the next part, which is please choose the plane orientation. Okay, the indication here, you will see it in the forms of several colors. If the color of the statement is red, that means the simulation cannot be done until this problem is addressed, this issue is resolved. So first we need to choose the plane orientation. Okay, if the color is green, that means no problem. If the color is orange, it's a warning sign. The simulation can still be run, but there are some errors involved lah, that you need to be wary of. Okay, so now under the variant here, so we are going to start with VC0, which is a new simulation variant, which is our base variant, and there are several options available here. So on the left hand side here, you have options on the main parameters. And then under main parameters, you have orientation. Orientation means activate. Okay. So we have a system, and we have all the others, detail losses, consumption, storage, and so on. So now I'm going to click orientation. Okay. If I click orientation, we have several options available now. Now the tilt angle refers to the angle of the module, how much tilt we want to put the modules. If I put it into 0, that means the module will be lying flat with respect to the ground. Okay, but for our location, or for most of the location, like if we put our module flat, it will be a disadvantage. Why? Because when there is objects, or for example water from rain hits the module, it's going to stay on the module, right? If we tilt the module, then if there are any like light, dirt, and so on, it can be washed automatically by rain. That's one of the advantage. But actually, the important thing about tilt angle is because we want to optimize the angle of the module so that we can get maximum amount of sunshine. Right? The perfect angle, yeah, the best angle by rule of thumb is actually dependent on the latitude. Meaning, for example, in Malacca, 2 degrees, right? So the optimal angle, if you want to get maximum sunshine throughout the year, is 2 degrees. But 2 degrees, if we measure, is too small. The slant is very low, almost negligible. Furthermore, if there are raindrops, the rain will accumulate on top of the modules, right? So we want to avoid that. So typically in Malaysia, the angle is around 10, 15 to 20 degrees. We set the angle. Actually, okay, we can play around with the values here. Okay, let's say now I put 15 degrees, yeah? I press enter. And it is indicated by the tilt angle here. And you can see at the bottom here, we have the option here, loss with respect to optimum. So it's negative 0.5. That means you already lose a bit, about 0.5%, if you tilt the angle at 15 degrees. Let's say I put into extreme, for example, 90 degrees. The loss with respect to optimum now becomes 56.4%. Very high. So that's why in Malaysia we don't see buildings we install solar panels as the wall. Yeah, because too much losses. Okay, so countries like Japan, like European, okay, because their position is further north of our equator, it's more logical because of the position of the sun, which is the explanation on sun position requires a special lecture session by itself. But here we can already get the idea. Okay, sometimes you are also limited by the constraint design. For example, you want to install on the rooftop. The rooftop already have specific angle, certain angle. So you can already put it here. Okay, so now let me put it as 15 degrees. So this is the tilt angle. The next one is the azimuth. Azimuth, I want to put it simply, is basically the angle referred to the compass. So 0 degrees means direct to the north, right? So direct to the north. So in this position now, plane tilt is 15 degrees, azimuth is 0 degrees. That means this is the position of the module. So for those in the meeting room here, this is the example. Let's say the front here is north and that is south. So this is your module. The module will be tilted 15 degrees. And the surface of the module will be pointed to the south. The advantages of this kind of configuration is that we know the sunshine, the sunrise and sunset is from east to west. So north, south, east, west. So throughout the day, we can obtain maximum amount of sunshine on this module. Okay. But sometimes in your design, you may not have the benefit of setting your own azimuth angle. Sometimes you want to install on rooftop, the rooftop already has specific angles you need to put in. So you can put, for example, now let me put the azimuth angle at 45 degrees. So this is the position of your module now. So that means now pointed towards the south, 45 degrees, tilted 15. What is the loss with respect to optimum? Optimum is around 0.8%. That means during the morning, when the sun is rising from the east, right? So the amount of sunshine that hits the module is not optimum lah. After that, okay. Right? Okay, what is transposition factor? Transposition factor is because our data, we use horizontal values. But when we want to analyze, we want to get the tilted values. So the process of changing from horizontal to tilted, we have a transposition factor. Right? And then here, optimization with respect to yearly, we have the option yearly irradiation yield, summer and winter. So because we don't have the seasons, we just stick to yearly irradiation yield lah. Okay, so now let me go back. The azimuth angle, let me put to 0. Okay, on top here, we have several options also available. Okay, number one is we have fixed tilted plane. This is the simplest one. And then we have several orientation. Several orientation is also common in Malaysia. For example, rooftop, you have some of modules you want to put like this. Some of the modules you need to put like this. So you can put here several orientations. Okay. Seasonal tilt adjustment. This one is based on countries either towards the north or south of the equator, where they need to change the module tilt angle depending on the season. Unlimited sheds. This one is typical for solar farm. So solar farm, you usually see the picture, you have rows of solar panels, right? So we need to make sure that when we put the solar panels in the rows there, the front row does not have shading on the back rows at any time throughout the day. So this is indicated by the yellow line here. So the distance between the front row and the next row, the second row, must be sufficient to avoid shading. So this one, we call it as sheds, S-H-E-D-S. Okay, and we have also tracking, but tracking is not important lah. So I'm going to go back and select fixed tilted plane. And I'm going to click OK. Okay, so now we see that the button orientation from red already turns green. That means we have settled the first part. Now we want to move to the second part, which is the system. Okay, this is the essence of our design process, which is we want to determine the optimum configuration between our solar modules and our inverter. Okay, so on the top here, we have the pre-sizing help. So we can pick either no sizing, or we want to set a specific amount of power, or we want to install based on available area. So we have these options. Okay, for now, I'm just going to click the planned power, and I'm going to select 10 kilowatt. Okay, at the bottom here, you'll see the instruction. After we have decided the amount of power, it asks us to please choose the PV module. Okay, so the area where we need to choose the PV module is here. So there are several sub options available. Either we want to pick those that are available now, or we can pick something from production of previous years, because some of the PV modules may already be discontinued. It's not available now, but it was available in the past. So if you have some old modules, you can try to search it from here. And you have very large list, or very huge database of solar panels available. If you don't have the solar panels available here, you can also input your own solar panel based on your data sheet. But that one is a separate topic lah. Okay, for now, let me choose sun power, and I'm just going to choose a sample solar panel. Let's say I pick 340 watt. No, this one is 48 volts. Okay, never mind. I just pick this one. 345. SPR X21 345 COM. Yeah, okay. Okay. So it already provides some information like the VMPP, voltage at maximum power point, and VOC, voltage open circuit. And it already provides the approximate number of modules that will be needed, which is 29. Okay, now we see the indicator here. Please choose the inverter model. The total power should be 7.7 kilowatt, optimal or more. Okay, we set our planned power to be 10. But it says that the inverter should be 7.7. Why? Does the audience have any idea? Loss, correct. Because of the losses. Now let me go back to the slide and show you what I mean. Okay, from the solar panel, we are going to connect to the inverter, and from the inverter, we are going to connect to the grid. So here are the types of losses that's already going to be experienced by our PV system. Most of the losses will be found here at the PV system itself. So number one, we have irradiance losses, which is losses due to reduced amount of sunshine reaching our module. The second one is thermal losses. Thermal losses is related to temperature. We have shading losses. I'm going to go into a bit of the theory after this. And then we have shading losses, array mismatch, dirt and dust. Okay, these are the losses at the module side. And then from the module to the inverter, we will have some losses, DC cable losses. This is mostly related to the voltage drop. So the longer your cable size, the larger your voltage drop will be in general. And then the inverter also is going to incur some losses. And then from the inverter to the grid or to our connection point, you also have some losses. But when we talk about the losses, most of the losses comes from the PV system itself. The cable losses and inverter losses are minimal, maybe maximum around 5% also, the total losses. Anyway, when we consider all the losses, the total system losses will be around 20% to 25%. Which is why, if you have a 100 kilowatt peak, now when you see the term, you have to differentiate when you see the unit kilowatt peak, that means that refers to the capacity of the solar system, solar PV system. Okay, but the output is actually going to be reduced due to the losses. So because we anticipate the losses to be around 20 to 25%, so our output will be only around 75 to 80 kilowatt AC. Okay, let's go into the theory of the losses a bit. Irradiance losses, I think this one is intuitive for all of us. So the amount of irradiance is going to be dependent on the sky. The clearer the sky, the more irradiance the PV system will obtain. So if we have clear sky, the irradiance may be close to 1000 watt per meter squared. So we are going to get maximum or high amount of current. But if we have some clouds, then the irradiance is going to be reduced. When the irradiance is reduced, current will also be reduced. So the relationship between current and irradiance is directly proportional and instantaneous. That means once the irradiance drop, the current will also drop at the same time. And this is a factor that we cannot control. So we just need to accept it as it is. So irradiance directly affect the current, but only marginally affects the voltage. Okay, voltage also increases, but as you can see from the graph, the increase from 200 watt to 1000 watt is relatively small. But for the current, irradiance double, current also double. Irradiance increases 5-fold, current also increases 5-fold. So irradiance directly affect current. And because power is V times I, that's why this one is important. Okay, the second one is the thermal losses. Thermal losses is related to the module temperature. So ideally, we want our module temperature to be cool, The temperature around 20, 30, that will be okay. But as the temperature increases, what will happen? The voltage will start to reduce. This is also a natural occurring fact for PV modules we cannot avoid. Okay, when the module temperature increases, voltage decreases. Current increases, but only marginally. Current we also have increased, but very small compared to the voltage drop. So this also have a significant impact on the power output because as temperature increase, voltage reduce. So that's why you see in Malaysia, the problem we have is even though our irradiance is relatively high, our temperature is also high. That's why our module performance is not optimum as we desire. Like European countries, they have like summer seasons and spring and autumn season where the irradiance can be high and the temperature is cool. During those times, they produce quite high amount of power. Okay, number 3. This is quite important, shading. So you can see from the slide, I'm going to show to you an example. If we have multiple strings and we have 2 modules shaded, and then we are going to increase the number of modules, 2 modules shaded, 4, 6, until all the modules on these 2 strings are shaded. And this is the graph that we are going to see. Okay, this is basically the IV curve for the system. So the power, this one is IV curve, and this one is the power PV curve, power and voltage. This one is the current and voltage. So for unshaded is indicated by the black line. If there are 2 modules shaded, is the orange line. 4 modules shaded is the blue line. Okay, and then we have 6 and 8. 8 means all the strings, all the modules in these 2 strings are shaded. Then we have the purple line here. So as you can see, the current will start to drop. The more amount of modules shaded, the faster the current will drop. At the bottom here, we have the power curve. You see the black line, if there are no shading, this is the ideal PV curve. But you see here, either 2 modules, 4 modules, 6 modules, or 8 modules, the shading profile is about the same, meaning that the peak amount of power that can be achieved is the same for all types of shaded modules. Okay, why? Because the series or the modules are connected in series. So it's like when it's connected in series, if one is shaded, then the rest of the performance for the string is affected. Like if you have a series of lamps, one lamp blows, the other lamps also turns off. Similar concept. It's not fully cut off. It's not an open circuit, but the current will be greatly reduced. So this is why we want to ensure as much as possible, we want to avoid shading. Even like in UTeM, we have one of our modules shaded by a lightning arrestor. During some times of the day, the lightning arrestor covers only a line on our module, but the drop can be 20% to 40% because of the series connection. Right? Okay, number 4, module mismatch. Okay, module mismatch happens due to several factors. Number 1 happens when output, the basic concept is module mismatch happens when output from modules are different. Okay, output from modules are different, like in the case of shading. Let's say we have the modules connected like this, and one of the modules are shaded. You need to understand from the PV system, the current in a string is derived by the lowest performing module. If let's say all the modules are okay, one module is a bit faulty, the current is going to be driven for the whole string is going to be determined by this lowest performing module. That is the concept. So if let's say one module is shaded, like this in this example, then the total current will be affected lah. That's why we have bypass diodes to compensate some of it, but still is going to be affected. Another factor that causes module mismatch is when you mix different types of modules. Okay, I encountered this one from one of my students who is actually a technician for a solar farm. So the solar farm has been operating for about 8 years now. And some of them, so they need to replace it. The original module is continued. They cannot find the original module. So they need to put in the modules now, the current available modules. They try to put in the same rating, like for example, 200 watt, also 200 watt. But because the voltage different, current setting different, so there will be slight losses in the system. If you use a bigger one, yeah, there's some theory involved. Basically, depends on the current of the lowest performing module. Yes. But also some other factors is going to affect as well. We need to see the type of solar module for us to comment on that. Okay, then next one, we have dirt. So dirt on module surfaces, this one is self-explanatory lah. Once the dirt is on top of the module, it will cover the surface. Once it covers the surface, it will reduce the amount of sunshine that reaches the inside of the PV module. Okay, the other factors, cable sizing. So we have DC cable losses and AC cable losses. So DC cable losses is mostly what we are concerned about. So the maximum voltage drop under current Malaysian standard should be less than 3% from PV array to inverter. Okay, and then we have this aging factor. Aging factor. So aging factor, just like I mentioned just now, it's due to the natural degradation of the PV module after years and years of use. Is going to be slightly reduced. Okay, let's go back to the software. So now let's select the inverter. So it says that please choose the inverter. The total power should be 7.77 kilowatt. This one is optimal lah. So let me choose. Oh, sorry. I need to turn off this one. Okay. Okay, select the inverter. So I just choose Huawei here. We can also have the option of generic. Yeah. If we don't want to have specific manufacturers, we also have the option for generic. So we can select depending on our required or desired needs. Okay, let me go back to Huawei. And let me choose, for example, okay, they don't have 7.7 kilowatt, but they have 8 kilowatts. So I'm going to choose this one. Let's say I choose this one. So now I zoom in a bit. Sorry. Okay, once I selected the number of inverter, it has already provided what is the optimum configuration for our system. So here it suggests that I use module. Each string has 13 modules in series. And I should have two strings lah connected for this inverter. Alright. So if the combination or if the configuration is ideal, then it's okay lah. Then you have the green color. Let's say now I increase, then an error starts to pop up. Say that if I use 14, there's some problems with open circuit voltage later down the road. Let's say I reduce. Okay, I use, for example, now 7. It's still okay, but the notification here states that the inverter power is slightly oversized, meaning that our system is slightly lower than it should be lah. So the inverter size, the inverter is larger than the amount of PV panels we are connecting to it. Okay. Okay. So I put back to 13. Let's say I put to 12, then we have another option here between 2 and 3. But if I change here, something else will change. Okay, if I put 4, then it says that the inverter power is strongly undersized. That means the inverter is very low compared to the amount of modules connected to it. So consider increasing overload losses limit in project settings. Okay, now let me go back to this connection here. Okay, if there are no indication, that means it's fine. Then we have here overload loss. Overload loss 0.0%, and we have P-norm ratio 1.12. P-norm ratio is actually the ratio between DC and AC. The ratio between the PV module and the inverter rating. The default setting in PVSyst is 1.3. If it's 1.3, it's still okay. But if it's more than 1.3, then it will produce an error and it will block you from running the simulation, like what I showed you just now. Okay, this is more than 1.3, so indicated in the red. So the overload loss is 3.2%. Here is colored in red, so we cannot continue with the simulation until we adjust the setting here or increase the limit for the P-norm ratio. Okay, for now, let's keep it simple. And let's use this one. Very good. Okay. So let me click OK. Anyway, just to highlight, when we select 10 kilowatt peak and we already selected the module, it already calculated the amount of area that is required to install this module, which is 47. No, not 47, here 42. Yeah, 42. All right, so let me click OK now. And then we click ready for simulation. Okay, we have already fulfilled the basic requirement to run the simulation. I just run the simulation now. Okay, so we have the initial results for our basic variant. So some graphs available. You can see the daily system output energy. You can see the performance ratio. You can see the system output power distribution and array temperature versus effective irradiance. There are also other graphs available. For example, if this one, if you are not interested in looking at the performance ratio and you want to select other options available, you can select this one. For example, let's say incident irradiation distribution. Okay. Some other options available, array power distribution, array temperature distribution. So these are several graphs available that you can choose from. Okay. So I'm going to select array temperature distribution running. Okay. And then we have the main results on top here. So our system production will be 12,000. Sorry, let me set this to performance ratio. So we have 12,537 kilowatt per year. This is the amount of energy that is expected to be generated from your system. This is specific production, performance ratio, okay, normalized production, and some of the losses. All right, so now I think we need to take a break, but let me finish by generating the report. Okay, so I click the report. So it's going to generate the report. You can export it and save it as PDF. So it's already available here. If you purchase a commercial license, then you don't have the watermark here, PVSyst education. That is not, it's not going to be there. For us, the watermark is there. Okay, so the project name, the variant, okay, no shading evaluation. Okay, system power 8.797 kilowatt peak. And so we have the second page, we have the project summary, which is the meteorological, the location, characteristics, and so on. And then we have the system summary. Okay, not much here because we are conducting a very basic system. And then we have result summary, produce energy, and so on, performance ratio. And then on the next slide, sorry, on the next page, we have this one, PV array characteristics, based on what we have designed just now. Right? So this is our solar panel that we have selected. This is our inverter panel, inverter that we have selected. So it gives the parameters lah. The total module is 26, the module area is 42.4, cell area is 38.3, and so on. Okay, array losses, this one we are going to cover after the break. Okay, this is the performance. We can see, for example, here, the normalized production based on the months. This is dependent on the meteo data that we have generated previously. So the highest amount of generation we see may be generated in the month of February. And during June and July, we should expect lower amount of generation. So this information is important for solar panel or solar PV owners, either solar farms or residential, because they can estimate the amount of money they get based on the amount of energy that is generated. Yes. Okay, so we can already anticipate this month how much we are going to get, right? Based on this profile lah. And okay, these are the meteorological data just now, right? And then the performance ratio. The performance ratio is actually the ratio between the actual divided by ideal. Actual output divided by ideal output. That means no losses. The with losses divided by without losses. So generally, if there are no losses, then performance ratio will be 1, right? But here, because of the losses from the system, we already anticipate the losses is around 20%. So this one here, based on our simulation just now, 17%, the losses. So our performance ratio is around 0.84 or 0.836. Right? Now this one is the important one that we need to understand, which is the loss diagram. We want to know for our system, what type of losses that we are going to experience. So that once we know that, we want to determine whether we can do anything about it, how to reduce it. Right? Okay, this for those without background in using this diagram, this is called a Sankey diagram. S-A-N-K-E-Y, Sankey. Okay, so on the top there, it shows the starting point, how amount of energy that can be potentially generated, until the bottom, what is actually generated. And on the right hand side here, it lists out the types of losses that is experienced by this system. So it is divided into two parts. The first part here is irradiance, is losses due to the irradiance itself. Then we have a separation here, and then we have irradiance due to the system. So at the top here, maybe not much we can do about, but at the bottom here, yeah, there's a lot we can do. Okay, so let's look at the types of losses, yeah. So starting, we get the irradiance, global horizontal irradiance is 1719. And then because of the position, yeah, because of the location itself, some losses is incurred. So we get 1652 kilowatt hour per meter squared. So the unit is different lah. This one is intensity. This one is power. Okay, so at the start, the array nominal energy, we should get 14,837 here. And then we have losses. Number one, we have losses about 1.8% due to irradiance. Okay, and then we have negative 8% due to temperature. Okay, if, you know, like temperature based on the location, there's not much we can do about it. But if the temperature is, for example, related to the module position, if the module is too close to the roof area, there's no spacing for wind to pass through. That means that there may be some areas we can improve on, but that is quite a detail lah. And then we have module quality loss 1%, module array mismatch loss 2%, ohmic wiring loss. Okay, ohmic wiring loss refers to the cable losses. Cable losses. And then inverter loss during operation. Okay, this is This is the losses because of the inverter that I have chosen. Okay, the rest, okay, we can say almost no losses lah. And then based on these types of losses, this is the amount of energy that we are going to get. Okay, these are the graphs that we have seen earlier during our generation. And this is the single line diagram. Of course, this is a simple single line diagram. But if you have a complex system, then there's a lot more we can do with designing the single line diagram. Okay, so I have covered now from start to finish how to generate the report and how to understand the basis of the report. So I would like to take a break, but let's now open if there are any questions from the... let me see the question. If I touch the open circuit PV module with my bare hands, which part are you touching? If you touch the module itself, no. If you touch the cable, the conductor behind, and the conductor is not insulated, I mean, you touch the copper itself directly, and the module is under the sunshine, and you touch both the positive and the negative conductor, yes, you'll be electrocuted. It's extremely, extremely dangerous. You see, just for information, yeah, the PV modules itself is a current control device, meaning that the amount of current is only limited by the module characteristic itself. Okay, for example, let's say the typical monocrystalline module, the short circuit current is about 8 amps. 8 amp, The amount of current that is required to stop your heart is only about 50 milliamps. So if you touch the positive and negative conductor of the PV modules directly, then current will flow in your body lah. But if you touch the module itself or the body of the module, no problem, inshallah. How can we put different panel on a different MPPT on the... Actually, no problem. When we have different MPPT, that means it's as if they are separate inverters. Let's say you have a 10 kilowatt inverter with 2 MPPT. It's essentially like you have 2 5 kilowatt inverter operating separately. The only thing is that it's installed at the same device, under the same device, but it operates separately. Okay, for the benefit of the crowd, those who don't know what MPPT is, MPPT stands for Maximum Power Point Tracking. It's a power electronics circuit that allows the inverter to determine the optimum point of electricity generation based on the irradiance and temperature level. Because the irradiance always change, right, throughout the day. So the inverter has the capability when the irradiance rate increase, okay, they can find the maximum power point. When the irradiance drop, they can find the new power point that produces maximum power. That is MPPT. So now the current design, we have multiple MPPTs. Multiple MPPTs. Okay, if I go back to the software, let me close this report. I would like to save this report first. Yeah, I think I can save this one. I don't have to save it as PDF. I'll just save it here. Okay, I'll save it. Okay, then I close. Okay, let me go back to the system here. So when we go to the inverter, you have the option here. Inverter use multi MPPT feature, and for the inverter I've chosen, it has 2 MPPTs. We use different MPPTs because we want to isolate. If let's say one system is faulty, you don't want to affect the whole PV system. So if one system is faulty, it's going only to affect the system that's connected to that MPPT. So the other MPPT is not affected at all. The old design, when they don't have the MPPT, what happens? You have a large system, one module problem, the whole system problem. So now when we have multiple MPPT, at least you minimize the amount of area that is affected. That's the essence of MPPT. Okay, hope that answers your question. Next. We are working on it. We need to find the funder lah, actually, because our limitation is the budget. But as you can see, if we get the student license, we can get each license for 25 Swiss dollars. But we need to provide them with a curriculum, endorsed curriculum. And we need to prove to them lah that part. So we are working on it.
Okay, so the next one, based on the design, is it possible to obtain the actual data in the form of Excel file, for example?
You mean from PVSyst?
Yes.
I think can. Yes, we can. Okay, let me go back. Here. Let me open this one. Okay, at the bottom here, you have the option of export the table. Okay, so if I click that, the full monthly meter data is now copied into the clipboard. You can paste them in Excel or any other spreadsheet program. Okay, and let me show it to you guys. Okay, I need to do some conditioning of the data. Text to columns, I think. Comma, right? Yeah. Select comma. Okay, next. Finish. And yeah, you have the data here. Okay, so you go back to the export table option. So you can get the monthly data. Okay, next.
But is it possible if
hourly data, because it's synthetic generated, no, there will be no missing values because it's synthetic. Diagram. From the loss diagram just now, right? Let me check the report. Maybe he's referring to this one. Shading is going to be here, but because we don't consider in our basic design now, it's not here lah. We can see it lah. If we do the shading, it's going to be available here. Multiple year individual record. Multiple year. Currently for PVSyst, it doesn't generate for multiple year because it assumes the same profile is repeated. The cycle is repeated every year. But if you want to, for example, you have your own data. Every year your data of irradiance profile is slightly different. Then you can put in and run your simulation on your own. That is quite advanced, I think. But it's possible if you have your own data. Soalan.
A few insulation fault, like small piercing, we did cause the losses. And let's say the both positive and negative travel lane next to each other, fusing holes, lead causes of losses.
Okay. Okay, say Wahyudi, yeah. Talking about losses, actually, it depends on the types of piercing we're talking about. In PVSyst, the simulation is mainly focused on the voltage drop and the material of the conductor itself. I'll go into the losses a bit after our break, and I'll show you what are the parameters that we can simulate in PVSyst. But in general, when we talk about small piercings or piercing holes, it's not going to be visible in PVSyst for simulation. So maybe the simple answer is no lah, or negligible lah losses. Okay, so Mr. Wahyudi, we can discuss later on afterwards if you want to find out more. The simulation result and actual. Well, actual we can only get if you have the meter data lah. So this one is based on the design. So the design is based on several assumptions. For example, the assumption. Anybody turning on the mic?
Assalamualaikum Kiai. Aku yang tanya soalan ni sekali. Sorry, actually my real question was actually kalau katakan, have you ever done any like you use this PVSyst untuk let's say buat simulation on the actual system yang ada dekat FKE ke apa ke, and then compare, say for example untuk last year 2022 punya ke for the whole year, and then compare with the actual energy yang dimonitor, recorded dekat dalam kita punya sistem tu. How big is the difference between the simulated one dengan yang actual yang kita recorded tu?
Actually, we don't have that data. We don't have that data. Furthermore, kalau kita nak compare, if you want to compare, the data from PVSyst is actually a lot of them are assumed. Some of the parameters are estimated. So we want to compare. Of course, there will be some differences lah.
Yalah, maybe because I want to know what is the percentage of dia punya accuracy lah. Is it 70%, 60%, 80% to the actual reading of
I can say that the accuracy is more than 80%.
More than 80%, and then this is also based on some what do you call simulation actual data from yang daripada previous study pun ada buat juga lah maksudnya.
Ya, betul. Ya.
Oh, okay. Alright, okay. So 80%. Okay, thanks. Okay.
Thank you.
One important for two entities to try to save more power from the PV loads.
When we have two MPPTs, they operate separately. So if they are, if the characteristics of the irradiance profile is the same, then it can track the same amount of power. Tapi kalau, for example, if usually we have two MPPTs, if for example our module one MPPT, we have the modules in one direction, one orientation. The other MPPT we use for another set of PV modules at different orientation. For example, if we have rooftop, like this one, we want to install modules here and here. So let's say if the sunshine on the left hand side, during morning, so more the panels on the left side is going to produce more. Okay, and on the right hand side is going to produce less. If you use one MPPT, then the power is going to be derived by the lowest performing module. But if you use separate MPPT, that means this one is going to be optimized. And this one is unaffected. It's not going to affect this system. So that is the purpose of using, one of the reason we use multiple MPPT. So if we use two MPPT, both systems are facing the same direction, then it's going to track the same power. Right.
So the next one, in PV system, can we put different panel on a different MPPT of the same inverter?
Different panel, yes, can. Like I said, different MPPT is like we have two separate inverters combined together. So you can put different panels. Okay. IAM is related to the incidence angle modifier, which is dependent on the surface of the PV module. That one we postpone until after the break. I'll cover it when we go into the detail losses. Okay, from the floor, I think you can ask after our session. So now it's 10:53. Let's take a short break. 5 to 8 minute break. So free flow, there are some food available at the front of our meeting room. Please help yourself. And free flow, that means you can come take it here, no problem. Okay, so we have a short break. We are going to continue at 11 a.m. Thank you. Okay, Assalamualaikum and good morning everyone. We continue our session. Hold on, let me open back the software. All right. Okay, I believe we have a question from Okay, so question is from Mr. Muhammad Hazim. Yeah? Okay, question number 1. What is the best practice for DC AC ratio value? This is very subjective. For the same project, different companies may propose different DC and AC ratio depending on their design. Okay, so DC AC ratio, for the benefit of all the audience, like I mentioned just now, DC AC ratio is basically the ratio between the capacity of the PV system and the output of the inverter. So 1.5 meaning if the DC AC ratio is 1.5, that means, for example, if you have, if you want to produce 1 kilowatt at the AC side, you need to install 1.5 kilowatt at the DC side. So if you're talking about large scale, that means if you want to generate 1 megawatt AC, the DC AC ratio, if you put at 1.5, that means our PV systems need to be 1.5 megawatt. Okay, so according to Mr. Hazim, this is very high, which is generally true. Kita nak generate 1 megawatt, but we install 1.5 megawatt. So maybe from the perspective of investor, seems like a waste lah. Right? For similar types of ratio, I've seen different companies produce in the range of between 1.2 up to 1.6. Okay, this one is quite technical. Basically, it's based on the inverter clipping. Berapa banyak inverter kita nak, berapa amount of energy we are willing to cut off because of the peak here. Okay, let me try to explain it from our slide. Not directly from the slide lah, but if you see this figure here, the figure on the peak sun hour. Okay, so when we talk about the shape or the DC AC ratio, we refer to the curve, the bell curve here. Basically, if we set a higher amount of PV capacity, we are going to lose part of the energy at the top here. Okay, if we increase our PV capacity larger and we keep our inverter at a smaller rate, for example, just now, if let's say we want to generate 1 megawatt, we use 1 megawatt inverter, but our PV capacity is 1.5 megawatt. What happens, especially during the noon, the top part here some of the amount of energy here will be clipped. Clip meaning it will not generate power. So the ratio, sorry. Later lah. So some designers, they set very low 1.2 to ensure that very low amount of energy is clipped. Some companies are willing to cut slightly more. They cut they install slightly larger so that they can generate more at the bottom side here. I think this is quite technical. I need to use some whiteboards lah if I want to explain in detail. But anyway, if you ask me the second question, what is the maximum DC-AC ratio based on your opinion? I would say there's no definitive answer lah. There's no definitive answer. I would say I will also follow the range between 1.1 to 1.5, depending on the design, depending on the budget, and depending on the expected energy we want to generate. So question number 3, can we design different module orientations? Landscape portrait, sure, we can design different module orientation. Any effect related to power? No. Our orientation, if landscape or portrait, basically no significant effect on power. Maybe if there are effect very negligible. Okay.
So yeah. I also put on the attendance by which they will share their internet. So to record.
Yeah.
Can share the slide recorded after the seminar. So the next one, the last one, where can I get latest irradiation data for all states?
Latest irradiation data, I think SEDA has that data. Hold on. Let me try to Google it. I think SEDA, we have SEDA PVMS. Okay. Hold on, let me close this one. Okay. Okay, if you Google SEDA PVMS, you'll have this option here, SEDA Malaysia National PV Monitoring System web portal. I think you can get your data here. But I think it's paid. You need to pay some subscription. Okay, this is the website. So here is available up-to-date information, real-time monitoring, and reports about the solar. So here, subscription. There are some subscriptions available. So let's click on it. I haven't gone to this website for quite some time. I don't remember it. Here we can check meteorological data. Global irradiance, ambient temperature, wind speed, and so on, or irradiation data. So I believe you can find specific locations based on your requirement from this website. Right? Okay. So now let's move on, or let's continue our simulation process. I have already generated one base case for our project. So based on the available time, I want to cover maybe one part of another part, which is this here, detailed losses. So tadi ada soalan pasal ohmic losses and so on, right? Okay, so I'll try to cover that one briefly here. Okay, now let's go into detailed losses. I'm going to click detailed losses here. So this window comes up and it has several tabs. I think I also need to magnify this one. Can you see clearly? Okay, for the detailed losses parameter, we have options. Number 1, thermal parameter. And then we have ohmic losses. Okay, ohmic losses, which is the cable loss. And then we have module quality and LID mismatch. We have soiling loss, We have IAM. This one, there was one question just now about IAM losses. We have auxiliaries, we have aging, and so on, and unavailability and spectral correction. Let's go back one by one. Okay, this is the loss due to the thermal parameter. Basically, in PVSyst, for the losses, even without us doing anything, it has already do some losses assumption in our initial generation report generation just now. So there are already default settings available for the losses. Under normal simulation, you don't need to modify any of this. Any of the parameters here, you don't need to modify. Your result will still be valid with some tolerance level lah. Okay, so thermal parameter, we are talking about the temperature effect on the module. So here we have the terms on field thermal loss factor. So this one I don't intend to cover in the theory in detail. There's some related parameters here like UC and UV. For me, I'm just going to maintain it as it is. Okay, I don't intend to go into the theory on this one. Let's move on to ohmic losses. Ohmic losses is about the cable losses. So we have the option here. We want to determine the fraction of the losses for the DC and AC side. Right, so we can choose either we choose the global wiring resistance. We set the resistance value of our wiring, DC wiring, or we can set it as in terms of the loss fraction. If you remember, I mentioned previously that for the DC side, from PV array to inverter, under Malaysian standards, the cable loss should be less than 3%. So in PVSyst, the default setting is at 1.5%. So I don't see the need to change this one, at least for this application. Okay, and then we have another option, voltage drop across series diode. Okay, this one is also, I think we don't need to consider, at least for basic simulation. AC losses, excuse me. AC losses after the inverter. This one, if you want to put the length of the cable from the inverter to the injection point. Okay, we want to define the length. This one is especially beneficial for large-scale solar, where we have hundreds of meters of cables. We want the voltage drop might be significant, so we can put it here, and we can also select the cable sizing, which will also have an impact on the voltage drop. So the larger the cable size, generally the lower the voltage drop lah, and the lower the DC losses. This one is for AC, of course. Right? And then moving on to module quality and LID mismatch. Okay, module quality, we have the module efficiency loss. This one is usually also, I don't change this one. I use the default value. Basically, module quality, as mentioned here, is the deviation of the average effective module efficiency with respect to manufacturer specifications. So small impact. And then module mismatch losses, the default setting is at 2%. Okay, this is PVSyst recommendation based on their experience lah. Power loss at MPP, they say at 2%. When we connect modules together, even though the modules are from the same manufacturing batch, the same type, the same model, and so on, there will still be some differences because of the manufacturing process involved. There will be some deviations or some differences in the output, slight difference between the output of each module. So it's accumulated as 2%. Okay, light induced degradation, LID, is actually only affecting silicon-based modules, monocrystalline or polycrystalline. Okay, this is a phenomena that has been found that the module will have a reduced output, slightly reduced output, the first time it is exposed to the sun. Dia akan ada losses tu. Let me show you example. If I open data sheet, one sample data sheet. I think it's this one. Okay. Let me enlarge this. Okay, tengok This one is sample from JA Solar. You see the performance or power output warranty. You tengok dekat awal-awal ni, at the early part here, during the first year, already the efficiency dropped from 100% to 97%. It doesn't start at 100%. It already starts at 97%. So basically, this is what happens when the module is exposed to the sun for the first time. Dia dah akan ada losses dah. And this is the losses due to the specific nature of crystalline modules. When it's exposed to the sun for the first time, there are some chemical reaction involved inside there. Okay, adalah technical lah, dia theory sikit lah. That will cause the efficiency to automatically reduce to 97%. Depending on the manufacturer, some 2%, some 3%. So this is the effect of light-induced degradation. Okay. For PVSyst, they assume that this LID is negligible. We don't put it. But if you desire to put it, depending on your module type, you can put. If, for example, like right now, I use the module from JA Solar. So the LID loss factor is 3%. So I can put it 3% here. Okay, and then the strings voltage mismatch. This one is also very, very small effect for PV modules. So we usually set it at 0. Okay, and then soiling loss. So soiling loss is basically for our location in Malaysia, we usually set to 0. But if the system is located in areas that is prone to dust, for example, near desert climates, or maybe near oceans or near beaches where there's a lot of sand, so maybe you want to consider this one. In general, I don't think they have a standard on what are the percentage level for the soiling loss. There are some studies, but there's no standard. So it's up to us. We want to put how much we want to put. Generally, if you want to be on the safe side, we want to be conservative, we put around 5%. The losses due to soiling. Okay, but default setting in PVSyst is 0. Okay, incidence angle modifier. This one, to be honest, I haven't used it in my simulation. This one is actually related to the type of the solar panel itself. Okay, if we disable the user's definition of the PV module, we have some options available. These options is actually dependent on the type of coating of the solar module, the type of glass that is used on the solar modules. So the type of glass basically affects the reflectivity of the sunshine from the top of the glass into the chemical reaction inside the solar panel. Right, so this is the incidence angle modifier. Generally, even if we look at PVSyst experts themselves, they don't modify this directly here. Instead, they do some detailed study where they change the values accordingly. Okay, then we move on to auxiliaries. So auxiliaries refers to the elements that is required for the system to function. For example, like solar farm, maybe you have the use of air conditioning units, you have the use of fans, maybe you have used some electronic devices, and part of the energy from that devices used to run the PV system is consumed from the PV itself. So this is categorized under auxiliaries. So let's say I select here auxiliaries consumption defined. So I can put what are the capacity or the watt that is going to be used from our PV system. So basically the auxiliaries is because when we have systems that part of the energy we use ourselves and the rest we export to the grid, we want to only calculate the amount of energy that we export to the grid to determine the accurate amount of ROI or the accurate amount of money we are getting back. Okay, this is the function of auxiliaries. Right, and then we have aging. Aging basically macam saya cakap tadi, like what I mentioned, we want to know after, for example, a few years, what will be the expected output after the degradation. If I go back to the slide, to the PDF just now from the module datasheet, for this module, it already mentioned that this is going to be the profile of the power output throughout its warranty. So this company guarantees that their power output will be linearly reduced. Okay, from 97% at year 1 to maybe I think here around 82% at year 25. So I would say we can expect that every year due to aging, the performance will drop about 0.5%. Or we can say that the performance due to aging will drop about 1% every 2 years. This is the general rule of thumb. And this losses is only on module, not on the system. All right. So however, the aging itself will consider the whole system. So we have some options here. Let's say I select users in simulation. So we can select here, for example, simulation for year. How many years we want to simulate? Let's say we want to simulate for 10 years. Okay, what will happen? What will be the degradation profile after 10 years? And then we have the individual PV modules global degradation factor. Okay, this one refers to the PV modules. And then this one refers to the mismatch degradation factor. So the default setting, module aging parameters is set to 0.4% per year. I said just now, the rule of thumb generally 0.5% per year. So this one is set at 0.4. Okay. And some other settings available. If you want to study more than 10%, more than 10 years, and depending on this one, we can also put in module warranty. Okay, this one, if you have the database of the PV module, I think this one is going to be automatically inserted. But I'm not sure. I need to check back. Okay, for now, I'm just going to maintain as it is, this value. Okay, unavailability. Unavailability refers to we expect throughout the year there may be some downtime for our system. Maybe unexpected shutdown. Maybe we need to do preventive maintenance or corrective maintenance, which will during that time the PV system will not export energy to the grid. Right? Typically, maybe 1 year we expect maybe 2 or 3 days of downtime, possibly. So we can put it here. We can put it either unavailability duration days per year. If we know, for example, throughout the year, there will be 5 days where the system will not be functioning. Or if we don't know, we can put it as in the form. Let's say you assume that throughout the year, maybe 2% of the time, there will be unavailability. So you can put it in terms of percentage, and it will randomly determine the shutdown time from the simulation. Right? Okay, we can also set a number of periods based on our definition lah. Okay, and then spectral correction. Spectral correction is basically for monocrystalline, not applicable. We don't need to do any spectral correction for monocrystalline. The only module that I know requires spectral correction is cadmium telluride. Okay, cadmium telluride requires some spectral correction. It requires some external data input from solar anywhere. Okay, that's beyond our discussion for today. Okay, so now let me show you what happens if I want to compare a different variant. I want to do some changes in the design, and I want to see what is the difference on the output from my changes to the original design. Right? So I'm going to keep it simple. For now, I'm going to keep the losses as it is. I'm just going to change the orientation. I'm just going to change this variable only, just to see what will be the difference. Okay, so let's say now I put the plane tilt instead of 20 degrees, I put it as 50 degrees. Right? And then the azimuth angle, instead of the ideal 0 degrees, let's say I put it as 60 degrees. Right? So now we already see that if we look here, loss with respect to optimum is already very high, 16.6%. But for the purpose of simulation, I'm just going to run this to show you how we determine the differences. Okay, I click OK. Right? And then I want to sorry, I think I need to go back. Some slight mistake here. I go back to the original one, 15 and 0. Okay, I want to select a new variant. Yes. Save. Yeah, let me try first. I don't quite remember. Let's say this is 60. Okay. Yes, I'm going to save this as new. Okay. So previously I set the tilt angle to 15 and azimuth angle to 0. Now I change the tilt angle to 50 and azimuth angle to 60. I click OK. And when I want to save, I want to save it as a new variant. So instead of clicking save, I'm going to click save as new. So it's going to save under a new variant, which is demo seminar UTeM, but the extension at the back here now is VC1. I click OK. Okay, I'm going to run the simulation again. Okay, I run the simulation again and I generate the report. Okay, so this is the report for the new variant. What I want to do now is I want to compare what is the difference between this variant and the previous variant or the previous original simulation I did just now before our break. So here we have the option of compare with another project variant. Okay, I click this one and I can select the one that I have run earlier. Click OK. Oh, I haven't run the simulation again. I need to run the simulation, is it? Okay, hold on. Let me close. Yes. Save, yes. I think I already saved this one, but okay, never mind. I'll just run it. I'll save it. Okay, this one, save. And close. I click again. I run again. Okay, already done. Right. So I go to the report. Okay, compare with another project variant. Let me select this one. Okay, so now it produces the two reports side by side. So the left hand side is the new variant and this one is the old version. So we have the option of highlighting the difference. Okay, we can compare. What are the difference in these two reports, the changes that we make. So you see here, the difference is that we can already see I cannot. Okay, we can already see that the changes we make is at the tilt and azimuth angle. Previously, it was 15 and 0. Here it's 50 and 60 degrees. So you can already see that the amount of power that is reduced, that is produced is different because of the change in the tilt and azimuth angle. So previously, when we have our ideal tilt and azimuth angle, the energy produced is 12,730 kilowatt hour per year. Now, when we change the tilt angle to 50 and 60 degrees respectively, the produced energy drops to 10,000. So we can use this comparison to determine and compare our different design process or design changes in parameters. So all of the difference are highlighted so that easily we can see the change, what are the effects of the changes that we have done. Right? And here we can see the changes in the losses as well. So remember, just now, on the left-hand side is for the tilt angle 50 degrees and azimuth angle 60 degrees. Macam mana kita nak? Kita tak boleh ke tepi. I'll just reduce it. Okay. So previously, when we have our tilt angle at 15 degrees, our loss due to the position of the module is only 1.3%. But once we change the tilt angle and the azimuth angle, now the losses becomes very significant, 18.64%. So this contributes to the losses lah. So maybe I need to do some correction with my earlier statement. We cannot do too much on the irradiance itself, but we can do something with regards to our PV module orientation. Right? Okay, and then IAM factor on global incidence angle modifier. Okay, only slight difference. 1.14, 1.22. And the rest, there will be some slight changes as well, despite we didn't do any changes for the system. Okay, so these are one of the benefits of having different variants. We can compare directly from the reports. We can also use this to, let me close this. We can also use this to study different systems. For example, just now, when we click at the system, we choose this type of module and this type of inverter. So let's say we want to change. For example, we want to use other types of module manufacturer. Let's pick something at random. Not too random lah. Maybe I pick something like Long E. Okay, Long E Solar. We have the company here in Malaysia. Not updated. Okay, let's say I pick 345. Okay, maybe I choose another inverter. Let's say Fronius, and I select something similar, 8 kilowatt. Okay, so I'm not going to change anything else because I just want to show you the difference. Okay, we want to compare, for example, between this type of inverter and module combination to get compared to the previous module and inverter configuration. Okay, some errors here. Inverter with 2 unbalanced MPPT. Okay, I think it's okay. I can use it. Okay. Okay, there's some problems because it has more than 2 MPPT input. Okay, so I need to choose another one maybe. Okay, let me check. Oh, cannot use this one. Maybe I'll just choose some generic inverter. I pick 8. Okay, and I click OK. Close the sizing anyway. Never mind lah. I think I'm just going to change the module. I'm just going to stick with the same type of inverter. Same manufacturer. Okay. Click OK, ready for simulation, and let's run the simulation. Okay, we get some output. We can use it to generate the report. And then we can compare. Okay. So again, we can see the differences. Not much differences we can see because we don't change the inverter profile. But these are just the sample of what we can do when we have changes in our variant design and how it affects the overall system. Let's say for now, okay, I want to include some of the losses. I want to study, for example, the aging factor. Some projects, they require you to also simulate for, long term, 10 years, 20 years, what will be the expected output. So let's say I want to use this in simulation. I set the simulation for 10 years, and let's say I set the degradation factor at 0.5%. Okay, so now we have included the aging factor inside here. So we click OK, and we run the simulation. When we produce the report and we compare with the original one, we'll see that on the left-hand side, see, it's not there. Here, we have it here, module degradation loss for year number 10. So previously it's not available in the original one because we didn't do aging analysis. Here is already considered. The module degradation loss for year number 10 is at negative or minus 4.75%. So these are the features that is available in PVSyst that you can play around to get the system performance based on the types of losses that you want to consider. Okay, so now it's approaching 12 o'clock already. I think I have covered most of the things I want to cover. So maybe I can open to questions from the audience or from online, if any. Okay, do you have any questions from members of the floor? Okay, maybe I'm going to touch a bit on economic evaluation. Yeah. If we look at this window here, there is an option on the right-hand side here, which is economic evaluation. So if I click the economic evaluation, this window will pop up and we can put inputs into this window based on our system cost. Okay, so the values, the currency we can actually select. There's a multitude number of currencies we can select. So I've already set the default setting for me for Malaysian ringgit. We can determine the current. I'm not sure whether this is current rate or not. I think it's current because we can update the rates. Right? So we can get the actual current rate for each of the currency. For the values, we can use either global values for the calculation, or we can calculate by watt peak, or we can calculate by area, meter squared. So we can key in other values. Okay. For example, let's say this module, we need to use 26 modules. So I'm not sure what is the current price at the moment. We can put in the values here, and we can put in values for all the components that we use as well, the inverters, other components. Studies and analysis. This one is if you are some outside consultants to do the necessary groundwork. Installation costs. Okay, involving all the transportation and so on. Insurance. So it's quite a detailed forms available here for you to do your economic analysis. Okay, land costs for purchase or for rent. And then loan bank charges. And then taxes. Okay, so you can put in as many values as you have to get the most accurate economic evaluation. Then once you put in the values here, it will calculate the amount of operating costs here. Okay, this is the first tab. And then the second tab, the financial parameters we can set. For example, the simulation period. How long is the project lifetime? What is the expected inflation rate or discount rate? This is related to the amount of investment lah, the value of money over time. Right? And then production variation, aging and so on. And then electricity sale. So if you want to calculate based on, for example, the amount of energy that we are generate and the amount of money we are getting paid. So we can put in the rate here. So this applies, for example, for fixed in tariff projects or for large scale solar projects. You can key in, we can put in here, and it will automatically calculate the amount of money that you can get based on the amount of energy that you generate. Right? So it can be either fixed tariff or variable tariff. So for our case, it's fixed tariff lah, but some countries, they have variable tariff depending on the time. So during peak time, usually the price is more expensive compared to off peak. Okay, so we can put it as well if you desire, and you can get the financial results here. Okay. So the financial result is quite comprehensive. You can already see what are the capex and opex, as well as your ROI. But I'm sorry, I haven't prepared any sample cases for us to run for our session today. So this is just an overview of the capability of economic evaluation. Right? Okay, maybe one more thing I would like to highlight before I end this session is we also have some capability to run multiple variation of simulation. Okay, for example, now at the simulation box, we have the option for advanced simulation. I'm going to click this now. And we are brought to this window. Under this window, we can see that we have the option for batch simulation and optimization tool. Okay, optimization tool, if I click this one, we are given this one. We can run 3 separate parameters to see what are the changes for each of the parameters and what is the effect on the system. If I click this one, I have the option for tilt and azimuth. Okay, just now I just pick 15 and 50, the tilt angle. But what if I want to study between 15 for every 5 degrees time step? I want to know what is the difference for each time step. I can conduct it here. So I can select tilt angle. I can select, for example, the minimum now was just now from 15 to 50. So the steps, okay, it sets to 6, but we can modify. For example, I want the steps to be, let's make it simple. I start from 0 to 50. I want it to change every 5 degrees. So it requires 10 steps. 11 steps, including 0. Okay, but then our simulation will be long. So maybe I'll just run for 5 steps. Okay. So I just change the tilt angle. I want to run for each 5 degree time step. What will be the differences? So I'll just run this. Okay, and click OK. So we can view the results. And this is the result, the energy power output based on different tilt angles. So we can see, okay, these are the changes and these are the relative power output with respect to the change in the tilt angle. So sometimes we want to use this to determine when we have the option between this and this, we want to choose the range, optimal range. So we can conduct in this type of form to get the optimized level. Right? And if we want to run more than 3 cases or more than more parameters, we can do this batch simulation. But this one, it's not for the demo today. I'm just going to provide overview for batch simulation. If you want to run really a lot more parameters with a lot more simulation, then we can use batch simulation. But then the processing time will depend on your computer strength lah, computer processing capabilities. Right? So these are some of the options available in PVSyst. And apart from the main parameters, there are also optional parameters. So under optional parameters, we have, for example, horizon. Okay, if I click horizon here, this graph will come up, and this graph will basically provide, you know, like what will be the irradiance profile based on our location. compared to the horizon. Because some areas, the horizon will have an effect on the sunshine based on the tilt angle. For Malaysia, I can say that the effect is not so significant. Tapi kalau macam European countries, kan, countries located further to the north, they will see the sun much lower because of the position. When the sun is at the equator, they are at the north, they are going to see the sun much lower. When you see the sun much lower, that means if there are very high objects like mountains, then it will be covered. This is what meant by horizon. Horizon study. For Malaysia, our case not too significant because our sunshine is always we see above our heads. Okay, and we also have near shadings. Okay, near shading, this one we can do a construction or perspective. We can actually draw. Okay, kita buat bangunan, kemudian kita simulate okay, apa objek yang ada di sekeliling. We have buildings maybe and trees and so on. So maybe for example, let me show you one sample case from the demo file already available in PVSyst. Let me run this one, demo residential system at Geneva. Okay. Because there's already some files available there. Okay, if I click near shadings and I click the construction perspective, there's already some figures available there. Okay, this is the location of the building and this is the position where the solar panel is going to be installed. So we can render. And then we can run the shadings animation. Okay. Let me go back. I go to near shadings. Okay, and then from this window, I click construction perspective. Because I'm using a demo file, the file is already there. If not, if you're using a new file, then you need to design from scratch lah. Okay, and then from this setting, I click here, tools. And under tools, I click shadings animation. So I can conduct a shading animation profile. To see throughout the day how much shading will affect the PV system. Okay, so this one is quite advanced lah. The shading part, even maybe I can say I am not well versed as well as in the shading part for the design. I only have basic knowledge on shading. Right? Okay, so this is also available in PVSyst if you want to do detailed shading analysis. Okay, so now it's already 12:07. We have already gone past 3 hours. I think I've covered the main things I want to cover. So are there any questions? No. Okay. Any questions from the crowd? No? Okay, so if there is nothing else, I would like to end the session here. I would like to thank all the participants who either have come to the meeting room here. Okay, we have participants even from Terengganu coming, very surprised. And we also have 100 plus participants from online, 130. And I think the participant was consistent throughout the session. So I really hope that you have benefited from the knowledge sharing session. And the slides, I think Dr. Arfa will help me share. And I will provide my contact numbers and contact data, contact information if you like to discuss further. Maybe you want to do collaboration, maybe we want to discuss some research work together. Please contact me. And I will be happy, inshallah, to entertain you. Okay, thank you for your time. Assalamualaikum and good afternoon.